Hello and welcome back. In today's video I'm overclocking the AMD Ryzen 9 7900 X3D Raphael CPU all the way up to 5789 MHz using the GIGABYTE B650I Aorus Ultra motherboard and EK Quantum custom loop water cooling. I picked this motherboard because I wanted to see what X3D overclocking is like on a more mainstream offering. Also, I kinda just like ITX solutions. Unlike the first generation of X3D CPUs, the 7000 X3D CPUs are actually overclockable, but that doesn't mean that they're easily overclockable. Alright, we have a lot to cover in this video, so let's get started. The AMD Ryzen 9 7900 X3D CPU is part of the third wave of AMD AM5 desktop processors. The first wave of Zen 4 Ryzen 7000 processors launched on August 29, 2022 and consisted of 4 X SKUs ranging from the 6-core Ryzen 5 7600X to the 16-core Ryzen 9 7950X. The second wave of Ryzen 7000 processors launched on January 4, 2023. It consisted of 3 non-X SKUs ranging from the 6-core Ryzen 5 7600 to the 12-core Ryzen 9 7900. The third wave of Ryzen 7000 processors, announced on January 4 but only available since February 28, consists of exclusively X3D variants with 3D V-cache. The lineup consists of 3 SKUs ranging from the 8-core Ryzen 7 7800 X3D to the 16-core Ryzen 9 7950 X3D. We already overclocked the Ryzen 9 7950 X3D in SkatterBencher number 56, and the 5800 X3D in SkatterBencher number 39. The Ryzen 9 7900 X3D is like the 7950 X3D, a dual CCD processor with one CCD featuring 3D V-cache technology. I won't say too much about the technical aspect of 3D V-cache, as plenty of other media will cover that part of the X3D story. Long story short though, AMD has 3D stacked additional L3 cache on top of the CCD to expand the on-die cache capacity. That, in theory, should help improve the performance in latency-sensitive workloads. The Ryzen 9 7900 X3D has 2 8-core CCDs, of which 2 are disabled, totaling 12 cores with 24 threads. One of those CCDs has V-cache, while the other doesn't. The base frequency is 4.4 GHz, and the maximum listed boost frequency is 5.6 GHz. The TDP is 120 watt and the PPT is 162 watts. In this video, we will cover 3 overclocking strategies. First, we rely on AMD PBO and EXPO performance boost technologies. Second, we use the GIGABYTE PBO enhancement feature in the BIOS. Third, we tune precision boost overdrive with curve optimizer. But before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The Elmo Labs Easy Fan Controller is the base version of the EFC SB that I showed off a couple of videos ago. I explain how I use the EFC and EFC SB in a separate video on this channel. Long story short, by connecting the EFC to the EVC2 device, I monitor the ambient temperature, water temperature, and fan duty cycle. I include the measurements in my Prime 95 stability test results. I also use the Elmo Labs EFC to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. I use this configuration for all overclocking strategies. The main takeaway from this configuration is that it gives us a good indicator of whether the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we jump into the overclocking, of course we have to check the performance at default settings. Please note that on this CPU, the AMD Precision Boost 2 boosting algorithm governs the CPU operating frequency and therefore also the performance. The standard parameters of the Precision Boost algorithm for the Ryzen 9 7900 X3D are as follows. These values don't tell the whole picture of how Precision Boost works on the 7000 X3D processors, however. I'll get back to that later in the video. Here is the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. When running Prime 95 FFTs with AVX512 enabled, the average CPU effective clock is 4275 MHz with 0.933 volts. The average CPU temperature is 61.2 degrees Celsius. The ambient and water temperature is 24 and 38.7 degrees Celsius. The average CPU package power is 105.8 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4578 MHz with 0.997 volts. The average CPU temperature is 74.5 degrees Celsius. The ambient and water temperature is 23.5 and 28.5 degrees Celsius. The average CPU package power is 115.1 watts. Now let us try our first overclocking strategy, but before that, make sure to locate the clear CMOS jumpers. Pressing the clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. However, it does not delete any of the BIOS profiles previously saved. The clear CMOS button is at the motherboard's bottom, right above the PCIe slot. In our first overclocking strategy, we will make use of AMD's performance maximizing technologies, PBO and EXPO. However, before we jump into figuring out what PBO is and what it can do for us, let's have a closer look at the Precision Boost 2 technology. For what I'm about to explain about PBO and how to use PBO to overclock, it's vital to understand how Precision Boost 2 works. Precision Boost 2 is an automatic performance maximizing technology available in all AMD Ryzen processors since the 2018 Ryzen 2000 series. This technology improves the system performance by dynamically increasing your processor clock speeds beyond stock depending on many factors, including temperature, power consumption, current draw, and the number of active cores. The fundamental building block of the Precision Boost 2 technology is the SMU or System Management Unit. Each chip on your Raphael CPU has an SMU, meaning there are 3 SMUs on a Ryzen 9 7900 X3D CPU. One of those SMUs functions as master SMU, while the others work as slave SMUs. Typically, the SMU in the I/O die would be the master SMU. All SMUs are connected using a low bandwidth control bus called SCF or Scalable Control Fabric. The SMU has a range of capabilities, including, most importantly, the ability to manage the CPU performance within the infrastructure constraints. The infrastructure restricts the maximum operating limits on various metrics, including power draw, temperature, and voltage. The primary function of the slave SMUs is to capture the measurement data related to the infrastructure limits, then prepare that data to be sent to the master SMU. The master SMU's primary function is to analyze the package-wide measurement data and determine the actions needed for performance management. Each infrastructure limit has its algorithm and is managed independently by the master SMU to determine the infrastructure limited frequency. The firmware then selects the most constraining limit as the global frequency limit. Then either of two things can happen. The current frequency exceeds that limit, or it doesn't. If it does, the frequency is reduced, and if it doesn't, there's frequency headroom and the frequency will increase. Either way, the master SMU passes the frequency change request to the slave, and each slave applies the frequency changes to the CPU cores of the local die. The frequency changes are also coordinated with the global voltage plane by the master SMU. Now comes the part that's important for understanding Ryzen 7000 X3D overclocking. Every slave can make independent decisions based on local conditions. So it can apply lower frequencies than the frequency requested by the master SMU if the on-die conditions require so. The Precision Boost algorithm has many infrastructure limiters, some of which are even exposed to the end user. Please note that while all of these limiters are present on Ryzen 7000 CPUs, it doesn't mean that they're all active or configured. Furthermore, the limiters for the CCD0, the one with Vcache, are severely more constraining than the ones for the CCD1, the one without Vcache. Here's a list of the Precision Boost limiters we're aware of. I discussed these in my Raphael Overclocking What's New launch video, so I'll only discuss the relevant ones for the Ryzen 9 7900 X3D. The main limiter constraining the Ryzen 9 7900 X3D is the voltage limit. As you can see from the table, the VID limit for both Ryzen 7000 X3D CCDs is lower than that of a regular 7900X processor. Furthermore, at 1.2 volt, the voltage limit for CCD0 is significantly lower than for CCD1. Raphael only has one VDD-CR voltage rail powering the CPU cores in the CCDs via the VDD-CR CPU voltage rail. It means that when any core in CCD0 is active, it will also restrict the maximum voltage for the cores in CCD1. That will also constrain its operating frequency. Note that this voltage limit is the absolute limit at pretty much zero load. When we put a load on the CCDs, the voltage limitation is even more constraining. On CCD0, the one with the V-cache, the maximum voltage under a heavy load is a mere 1 volt. For the CCD1, the one without the V-cache, that maximum limit under an all-core heavy workload is 1.2 volt. Another limit constraining the Ryzen 9 7900 X3D is the Fmax limit. Unsurprisingly, the CCD with V-cache cannot run at equivalent speeds to the non-V-cache CCD, since the L3 cache operates at the same frequency. We also saw this with the Ryzen 7 5800 X3D, which had a 200 MHz lower maximum boost clock than the Ryzen 7 5800X. That concludes our shallow dive in the Precision Boost 2 technology. Now let's move on to Precision Boost Overdrive and get to tuning our CPU. With the launch of Zen 3, AMD introduced an improved version of Precision Boost Overdrive. They called this Precision Boost Overdrive 2. This toolkit, PBO toolkit, allows us to manually adjust some of the parameters affecting the Precision boosting algorithm. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the platform overclocking knobs from Zen Plus, PPT, TDC, and EDC, and processor overclocking knobs from Zen 2, Boost Override, and Scaler, Precision Boost Overdrive 2 introduces Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. AMD's stock values, which can be set by disabling PBO, the motherboard vendor values, which are programmed into the BIOS to match the motherboard VRAM specification and can be set by enabling PBO, custom values, which the end user can program by himself. In this overclocking strategy, we're just enabling PBO, whereas in next overclocking strategies, we'll actually start tuning PBO. We rely on the motherboard's pre-programmed PBO parameters by enabling Precision Boost Overdrive. We find that the following values have changed. For previous Ryzen CPUs, increasing the platform boost parameters substantially impacted performance, especially for the higher core count CPUs. For Ryzen 7000 X series CPUs, however, AMD's default platform parameters were relatively unconstraining. For the 7900 X3D, it's clear that the platform boost limiters are not the constraining factor. During a Prime 95 non-AVX workload, we see that the maximum values for PPT, TDC, and EDC are 115 watt, 96 amps, and 98 amps respectively. The main limiting factor for the 7900 X3D is the maximum allowed voltage for the V-cache CCD, which is around 1 volt under a high load. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that enables ubiquitous memory overclocking profiles for AMD platforms supporting DDR5 memory. EXPO allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting, so it saves you from lots of manual configuration. While our memory kit is rated at DDR5 6400, for stability reasons, I have to reduce the memory frequency to about DDR5 6000. Upon entering the BIOS, switch to the Advanced mode. Enter the Advanced CPU Settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Leave the Precision Boost Overdrive submenu. Leave the Advanced CPU Settings submenu. Set Extreme Memory Profile XMP EXPO to EXPO 1. Set System Memory Multiplier to 60. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, enabling Precision Boost Overdrive does little to improve the system's performance. After all, the CPU is primarily limited by operating voltage, not by any platform power parameters. Thanks to enabling EXPO, we get a performance improvement of plus 7.10% in Geekbench 6 Multi. When running Prime 95 small FFTs with AVX512 enabled, the average CPU effective clock is 4258 MHz with 0.934 volts. The average CPU temperature is 63.1 degrees Celsius. The ambient and water temperature is 26.1 and 31 degrees Celsius. The average CPU package power is 119.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4568 MHz with 0.996 volts. The average CPU temperature is 75.6 degrees Celsius. The ambient and water temperature is 24 and 29.5 degrees Celsius. The average CPU package power is 129.4 watts. In our second overclocking strategy, we make use of the GIGABYTE PBO Enhancement feature built into the GIGABYTE AM5 BIOSes. GIGABYTE's PBO Enhancement, formerly known as Performance Bung, is a performance-oriented technology that's available in, now I think, every GIGABYTE AM5 motherboard. It's really just a list of preset profiles that allows you to tune Precision Boost Overdrive. The presets tune two things in particular: the maximum allowed temperature and an all-core curve optimizer setting. For example, this strategy's 90 level 1 profile will set the maximum temperature to 90 degrees Celsius and an all-core curve optimizer of -10. However, since the maximum temperature of the X3D CPUs is only 89 degrees Celsius, it won't override that factory-fused setting. You can select your preferred profile based on the maximum temperature you're comfortable with and how well your CPU can undervolt. Note that PBO Enhancement doesn't tune the PBO limits, so if you want to maximize the performance using PBO Enhancement, you should also check if the platform power parameters like PPT, TDC, and EDC are set accordingly. Upon entering the BIOS, switch to the advanced mode. Set Precision Boost Overdrive PBO Enhancement to 90 level 1. Enter the Advanced CPU Settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Leave the Precision Boost Overdrive submenu. Leave the Advanced CPU Settings submenu. Set Extreme Memory Profile XMP EXPO to EXPO 1. Set System Memory Multiplier to 60. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. While the performance uplift after curve optimizing is not earth-shattering, it's nice to see we achieve slightly better performance across the board. We see the highest performance improvement of plus 7.88% in Geekbench 6 Multi. When running Prime 95 small FFTs with AVX512 enabled, the average CPU effective clock is 4343 MHz with 0.927 volts. The average CPU temperature is 61.7 degrees Celsius. The ambient and water temperature is 24.3 and 29.7 degrees Celsius. The average CPU package power is 119.9 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4653 MHz with 0.992 volts. The average CPU temperature is 75.8 degrees Celsius. The ambient and water temperature is 24.3 and 29.8 degrees Celsius, and the average CPU package power is 129.6 watts. In our third overclocking strategy, we will make use of the Fmax Boost Override and Curve Optimizer tools available in the PBO2 Overclockers Toolkit. Fused Maximum Frequency, or Fmax, is one of the limiters of the Precision Boost 2 boosting algorithm. Effectively, it's the global frequency limiter. It sets the maximum frequency for every of the cores in your CPU. Boost Clock Override, or Fmax Override, is one of the overclocker tools available in the PBO2 toolkit. It allows the user to override the arbitrary clock frequency limit between -1000 MHz and +200 MHz in steps of 25 MHz. It's available for both the CPU core clock and, if present, the graphics core clock. We need to make two important notes about Fmax boost override for 7000 X3D CPUs. First, the override only adjusts the upper ceiling of the frequency and doesn't act as a frequency offset. Ultimately, the Precision Boost 2 algorithm still determines the actual operating frequency. 2. CCD0, the one with the Vcache, appears locked from increasing the Fmax. So while setting a negative boost override to lower the Fmax works, setting a positive boost override to increase the Fmax doesn't work. The Fmax remains at 5150 MHz. As I already mentioned in this video, Curve Optimizer is an important new feature of the Precision Boost Overdrive 2 toolkit. Curve Optimizer allows end users to adjust the factory-fused VFT or voltage frequency temperature curve for each CPU core separately. The VFT curve is a unique curve for each core inside your CPU that defines the required voltage for a given frequency at a given temperature. Higher frequencies or higher operating temperatures require higher voltages. Curve Optimizer adjusts the VFT curve by offsetting the voltages of the factory-fused VFT curve. By setting a positive offset, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. You can offset the entire curve by up to 30 steps in a positive direction and up to 300 steps in a negative direction. Each step represents approximately 5 millivolts. The traditional approach to AMD Ryzen CPU overclocking is that you use a negative curve optimizer. Two things happen when you do that. First, you tell the CPU that it needs less voltage for a given frequency, and as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. Curve Optimizer is available on a per core basis, and just like with previous generation CPUs, that provides us with a real tangible benefit, as some cores can overclock further than other cores. The manual tuning process for Curve Optimizer can become quite convoluted because it spans a range of scenarios from single-threaded light workloads to all-core multi-threaded heavy workloads. My tuning process for this Ryzen 9 7900 X3D was as follows. First, I use a broad tuning approach to get a big picture understanding of the tuning opportunity. Then, I narrow the per core Curve Optimizer settings to achieve stability in a light workload. Then I verify the stability in an all-core multi-threaded workload. Lastly, I run through all my benchmarks to validate stability in a wide range of test scenarios. In my case, I used a per core Curve Optimizer setting ranging from -45 for core 9 to -5 for cores 0 and 6, and an Fmax boost override of +150 MHz. I will show you the BIOS configuration in a minute, but first, please note that Curve Optimizer settings are really CPU specific, so don't just copy the settings that I'll be showing in my video. Make sure you find the optimal settings for your CPU. The following table shows the boost profile for this specific CPU. We can make a couple of interesting observations. At stock, the boost curve shows a couple of cores running higher than the advertised boost frequency of 5.6 GHz. That's not unexpected, as we know the fused Fmax is 5.65 GHz, but it's still nice to see some cores over-delivering on their promise. Furthermore, we can also see that all Vcache cores run at their Fmax of 5150 MHz. After curve optimizing, we see a substantial frequency uplift across the board. Two cores almost hit the new Fmax ceiling of 5.8 GHz. Unfortunately, we cannot do much more to push the Vcache cores further, as Fmax override doesn't apply, and the cores were already running at their Fmax at stock. Upon entering the BIOS, switch to the Advanced Mode view. Enter the Advanced CPU Settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to motherboard. Set CPU boost clock override to enabled. Set max CPU boost clock override to 150. Enter the curve optimizer submenu. Set curve optimizer to per core. For every core, set curve optimizer sign to negative. For cores 0 and 6, set curve optimizer magnitude to 5. For cores 1 and 3, set curve optimizer magnitude to 15. For cores 2, 4, and 5, set curve optimizer magnitude to 20. For cores 7 and 11, set curve optimizer magnitude to 25. For core 8, set curve optimizer magnitude to 10. For core 9, set curve optimizer magnitude to 45. For core 10, set curve optimizer magnitude to 35. Leave the curve optimizer submenu. Leave the precision boost overdrive submenu. Leave the advanced CPU settings submenu. Set extreme memory profile XMP EXPO to EXPO 1. Set system memory multiplier to 60. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. While the performance uplift after curve optimizing is not earth-shattering, it's nice to see we achieve better performance across the board. We see the highest performance improvement of plus 8.97% in AI benchmark, and here and there is a slight performance improvement in single-threaded and light workloads. When running Prime 95, small FFTs with AVX 512 enabled, the average CPU effective clock is 4,367 MHz with 0.929 volts. The average CPU temperature is 63.1 degrees Celsius. The ambient and water temperature is 25.7 and 30.9 degrees Celsius. The average CPU package power is 120.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4,670 MHz with 0.991 volts. The average CPU temperature is 77.2 degrees Celsius. The ambient and water temperature is 25.8 and 31.1 degrees Celsius. The average CPU package power is 130.4 watts. Alright, let's wrap this up. By choosing this particular CPU and motherboard combination, I wanted to experience what it feels like to overclock the 7000 X3D CPUs on a more mainstream motherboard offering. I call it mainstream because it has the B650 chipset and it doesn't support asynchronous E-clock. As you can see from this guide, my overclocking experience wasn't that great. And that's not because of a motherboard limitation. The motherboard is perfectly fine handling this 12-core Ryzen 9 7900 X3D CPU. You can see that the VRM temperature barely moves even when we throw Prime 95 AVX workload at it. No, the overclocking experience is limited because of the CPU. There's just not that many options available for tuning an X3D CPU. In fact, you are pretty much limited to enabling PBO, enabling EXPO, and then trying to maximize the frequency with Curve Optimizer. But the results are pretty limited. Anyway, as an overclocking enthusiast who enjoys the pursuit of the performance rather than someone who obsesses over the performance gains, this was still an interesting journey. I did learn a little bit more about X3D overclocking and the constraints that exists on, let's say, mainstream motherboards. Anyway, that's it for me today. I hope you enjoyed the video. I want to thank my Patreon supporters for the support. As per usual, I will also put up a written version of this video on my blog. And if you have any questions, feel free to drop them in the comment section below. And see you next time.